Okay. Um, yep, with the last few minutes, let's try and tie these two things together. So, okay, so let's put up let's give an example. Okay, let's define psi from Cn to the integers mod n by the rule psi of x to the n equals, or sorry, psi of x to the m is just the equivalence class of m. Okay. And actually the first thing, okay, so we want psi to be a homomorphism, but actually notice, so if psi from Cn to Z mod nz is a homomorphism, and I know that psi of x, well, psi of x to the 1 is just the equivalence class of 1. Then from these two facts, that psi is a homomorphism, then psi of x is 1, and the fact that x generates Cn, that determines what psi is. Okay. Then, for example, it must be that psi of x squared, well, that's just psi of x plus psi of x. That's just the equivalence class of 1 plus the equivalence class of 1. That's the equivalence class of 2. Okay. And this first equation is because psi has to take multiplication in Cn and kind of translate it to multiplication in Z mod nz, but the multiplication is really like the group law is addition. So it has to take the group law of Cn and translate it into the group law of Z mod nz. So it translates multiplication into addition. Okay, and so without telling you what psi of x squared is, we can deduce what psi of x squared is. And similarly, psi of x cubed, that's just psi of x times psi of x squared, or psi of x plus psi of x squared, and so on. Psi of x inverse has to be equivalence class of -1. Okay. Okay, there is kind of one hiccup that could happen. This is the problem of, you know, a function being well defined. Okay, so there is one problem. Okay. In Cn, we have the equation x to the n equals the identity. Now, if we were to apply psi, we get psi of x to the n equals psi of the identity. Well, assuming psi is a homomorphism, psi of the identity is the identity of the kind of codomain, which is the equivalence class of 0. Okay. But psi is also a homomorphism, so psi of x to the n is really equivalence class of x added up n times. And that has to be the equivalence class of 0. In other words, we need to have this equation. This must hold for psi kind of to be well defined. Okay. Okay. So basically, to define a homomorphism from Cn, we have to explain what is the value of psi on all the generators. Then we have to check that when we apply psi to all the different relations, the result is still true in like kind of the codomain. Okay. Okay, and let's just do an example where, you know, things don't work out. Let's call this like a non-example. We find psi from cyclic group C5. Remember, that's just a group generated by x satisfying x to the fifth is the identity. And we'll define it to Z mod 2Z. And we'll define it by psi of x. So x generates C5. So I only have to tell you what psi of x is. And then we'll just say it's the equivalence class of 1 in Z mod 2Z. Sorry, this is, hope that's better. Okay, so far it seems okay. You know, that tells me what is psi of x squared. Well, psi of x squared is just the equivalence class of 2. Well, in Z mod 2Z, the equivalence class of 2 is just the equivalence class of 0. Psi of x cubed, that's the equivalence class of 3, which is the equivalence class of 1. So far, everything seems fine. Psi of x4, that's just the equivalence class of 4. That's the equivalence class of 0 because 4 is congruent to 0 mod 2. Psi of x to the 5, that's the equivalence class of 5. That's the equivalence class of 1. Okay, but that's kind of a problem because x to the fifth is also the identity in C5. But the identity has to be mapped to the identity of Z mod 2Z, which is 0. Okay. So if I plug in x to the fifth, I get 1. If I plug in the identity, I get 0. But x to the fifth is the identity. So this is a problem. These are not equal. This is just a slanted not equal sign. Okay. Okay, so even though it seemed like I was doing everything right, I did the exact same thing as in the previous example. Everything crashed because I didn't remember that I have to check, I have to check that this relation holds when I apply my homomorphism to it. And, right. Okay. Okay, so that is why this is a non-example, because I didn't check that this relation holds, I don't get a well-defined function. Okay. Right, and again, that just means like I have two different values for the same argument. That's bad. Okay. Okay. And just if we go back to the example with Cn and the integers mod n, something nice happens. So for psi from Cn to the integers mod n, you know, we have psi of e, or in other words, x to the 0 is 0. Psi of x is 1. Psi of x to the I is just the equivalent, the congruence class of I. Right? We had this ends up happening. In other words, every element of Cn is matched up with one congruence class mod n. Okay, so we have a function, it's one-to-one and onto, and it's a homomorphism. So we give these a special name, we call them isomorphisms. Okay. So you have a definition. If phi from G to G prime is a homomorphism, such that phi is one-to-one and onto, then we call phi an isomorphism. Okay. And if phi from G to G prime is an isomorphism, we say G and G prime are isomorphic. And we write G isomorphic to G prime with like a squiggly equal sign. Good. Now, knowing that the Cn is isomorphic to Z mod nz, this is kind of useful. anything that I know about the group Cn, I can translate into the language of Z mod NZ. And anything that I know about the Z mod NZ, I can translate into the language of Cn, right? Because this gives me like a table of equivalences between the elements, right? And because its psi is a homomorphism, like if I add up two elements here to find the corresponding thing on the other side, I just have to find like addition on this side translates into multiplication on this side. Okay, so like, you know, here's kind of like a very lofty goal. Okay. Find all groups, let's say of order n up to isomorphism. Okay. Instead of find, I guess it's probably better to say classify. Okay. That means like for a given n, we might want to try and give a list of all the possible, like what any possible group can look like. So that like if I have any, so like for example, for n equals 10, I might want a list of groups such that any group of order 10 is isomorphic to one of the groups on my list. Okay. And then, you know, we could exchange order n for some other property. Okay. And let me tell you one fact before I go. Okay. First of all, that G is isomorphic to G. If G is isomorphic to H, then H is isomorphic to G. And if G is isomorphic to H is isomorphic to K, then G is isomorphic to K. Okay. So isomorphism of groups kind of acts like an equivalence relation. I'm not saying that it's an equivalence relation because of some set theory technicality. But okay, I guess that's it for today. I will try and have a new assignment and like more activities for you guys very soon. Okay, that's it for me for today. Thank you for all for coming.